My name is Marcus Brown, and I'm going to take you through kind of a tour of the SOLIDWORKS simulation standard, what you can do, and how you can leverage this in your designs. And in order to do that, we're going to cover four kind of main topics, four main areas. We want to talk about analyzing early and often. We want to use the software as soon as possible to make good decisions up front. And as we make those changes, we want to track our performance. You know, there's a lot of times people stop much sooner than they should have, and they had a lot of extra room for improvement. Other times you spend time just hitting the same issues over and over again and making no real performance. So I want to know when to stop and when to keep going and understand how to quantify that. I also want to talk about validating the final design. We need accuracy. We need to analyze things early, but then we need to kind of ramp up and step up the accuracy of our solution and our results so that when we submit a design, when we build a design, when we ship a design, we know it's going to work and we know what kind of performance we can expect. And then I want to talk about the complete system interaction, taking a look at the largest possible picture and show the real power built into the software. So we're going to start with early and often. Design and manufacturing costs are generally set in the first 20% of the design process. You set about 80% of those design costs by choosing materials, by choosing the overall shape, and everything kind of goes from there. So those early design decisions, although they seem like you're just kind of spitballing, they really do make a big difference and they lock you in. It's very path dependent when you do design. So what we want to focus on is making simple designs and checking those simple decisions early on to make better decisions. So I'm going to switch over to SOLIDWORKS and kind of show you what that means and introduce what we're going to do today, which is this case. Now, this case, it's about the size of a lunchbox, a little bit bigger, and it's going to contain this material. We're not sure exactly what, but we know there's some crazy stuff going on in there. Now, we already did this design, but we made everything out of plastic, and the load rating was 100 pounds. So somebody came back and said, hey, can we make a 500-pound lunchbox? And I don't know what in the world they're putting inside there that's going to be 500 pounds, but I said, sure, we can figure it out. So I did a pack and go on this assembly, and I created a new assembly made out of metal, because I'm assuming that we're going to have to make this whole thing out of metal. And I want to start making decisions on this handle really quickly. So I'm going to open up the handle, and we're going to start talking specifically about making decisions about materials. Now, I've got various design iterations. These are all kind of from the original design process. When we were doing it in plastic, we started out with something real simple, like a standard, lunchbox handle. We realized that wasn't going to work. So we started adding things like ribs and gussets, and decided it just needed to be beefier and beefier, and pretty soon we created something extremely beefy and then sort of trimmed it down to the final design. I'm going to back up just a little bit. I'm going to start with this design right here, and I'll show you how we can run some early design iterations to make decisions about materials. So I'm going to create a new study real quickly. This is just going to be called Material Check. And when you make a study like this in your part, these studies will stay in the part. So as you make changes down the line, or if you need to start over with something new, that's very easy to do. And it came in, my initial guess is that some kind of an aluminum alloy is going to work to build this part out of. Let's test that. So I'm going to fix the handle holes, because they're going to go into probably some steel dowel pins, so I'm pretty sure those are going to be strong enough. For the loads, we're doing 500 pounds, right? That's what it was when it was 100 pounds when we initially designed this part. So we're throwing 500 on that one face. All right, so there's our 500-pound load. Everything should be good to go. I'm just going to go ahead and run it. And again, we're looking at ballpark here. We'll figure out some stuff later as far as what we're going to do with the design and finalize the design. But should we even be in aluminum? Should we be in steel? Can we get the job done with aluminum, or do we need to go to steel? Or could we get the job done with a really good plastic? So my stress is way above yield. Of course, this is probably not the best aluminum, 24,000 psi. So let me change a different material here. I'm going to choose a different aluminum. I've got a 6061 here, and I'll run that one. Now you can see these runs don't take very long, right? We're very quickly able to make decisions, spitball, throw some things out, and say, yeah, that's going to work, or no, that's not going to work. So it looks like I'm at 24,000 psi on this baseline design. My yield strength is 40. So I'm not under a factor safety of 2, and I haven't even started to optimize the design yet. You really need to be beyond your factor safety that you need so that you've got some room to maybe streamline the design, change a few things for fit, form, and function. So that's just not going to work. Let's try steel. I'm trying to avoid going all the way to steel, but let's just see what happens if we make this thing out of steel. So I chose an 836, and that's kind of the same story. We're not getting a factor safety of all the way up to 2 or even beyond 2. So this design, fundamentally, we're not really in the ballpark. I don't want to go to anything more exotic than steel. So I do have another design, though, and this one is kind of our max. Like, we had a group of people come together and say, well, look, you can't go past this envelope. Look at this big old beefy handle. So I guess I've got to go up to the beefy handle and start from there. So I'm just going to duplicate this study for that much larger design. So this is beefy material check, and I'm just going to create a new study to run this, and nothing really additional is required, although I do want to see if I can drop back down to that aluminum, or if I'm going to go this beefy, maybe I can do nylon. Now you can imagine that if I had already gone through and started optimizing the shape, at this point I'd have already wasted a lot of time and opportunity to make some changes. I'm not going to get the job done with nylon. I'm betting I can get it done with aluminum, and if necessary, I'll jump up to steel. And it looks like with aluminum, our max stress is around 13,000 psi, yield strength is 40, so minimum factor safety is up around 3, and I need 2. So I'm feeling pretty good, right? I made some early decisions. I feel like 6061 is going to be the best solution. It's going to give me a lot of flexibility, but without being extremely complicated or hard to machine like it would probably be with steel. So now that I've done that, I've really made some big decisions quickly, and I'm ready to kind of move on to really bearing into the design, making really intricate design changes and things like that to try to make it better. And this is something that I've struggled with in the past, is knowing when to stop and knowing whether or not I've made it any better. And it's not always intuitive. Sometimes you make a design and change and it actually makes things worse. But probably even more sinister is where you spend all kinds of time and energy and money and you don't actually improve the bottom line. So we're going to use Trend Tracker to measure this and watch these trends and quantify the improvements. So we can say, oh, yes, we made this kind of an improvement and we're headed on the right track. So jumping back over into the assembly, we're going to go back to the assembly and start kind of running a few examples there. Now, I have a study kind of pre-created, and I'm skipping ahead a little bit because we went to the last design that we picked on the plastic part. So that 100-pound example seemed like the most obvious way to get the thing done, and this time was to just use that same design and put it into metal. Now the Trend Tracker is something that you just turn on. Just right-click at the top of your study and turn on the Trend Tracker, and it starts gathering all these iterations. I want to show you the results that I've done to this point because I have several results that I've already created. So this is the plot for the mass, and I also want to show the plot for the stress. I'm going to show these side by side so you can kind of get an idea of what this looks like. So here's my mass and my stress, and we started out in the plastic region. And when I say plastic, I don't mean deformation. I mean we were literally doing the 100-pound version of it made out of plastic. And you can see that the mass slowly went up as we made the strength high enough, and the stress went down. Well, then somebody said, hey, let's make this 500-pound version, and oh man, my stress went through the roof because I loaded up the 500 pounds so much, and you see I was trying to compensate. I was trying to chase the strength of the design, adding mass. And eventually we got to our maximum weight, and we managed to reach an achievable or usable design. And from that point forward, I've just been making incremental changes, trying to figure out which ones are going to work. And you can kind of see that the stress is trending up and the mass is trending down. So I'm at least headed in the right direction. So I'm going to make another design change and kind of see what that's going to look like. So inside Trend Tracker, you don't have to worry about keeping track of everything. Every time you run a study, it's going to make a capture and keep those records for you. And the next idea I had was just to make these vertical sections on the handle a little bit skinnier. So instead of 0.25, I'm going to do 0.18, for instance. And I'm going to see what that does. Right? Maybe it's going to get better, maybe it's going to get worse, but I'll run it. And again, it's going to be a quick study. I'm inside the assembly now, so I can take into account additional components if they're relevant. All I really did was attach these pins. And at the end of the results, the Trend Tracker goes and kind of takes screenshots of everything. It says, okay, well, let's kind of capture all this data, and let's see where we're at. 14,000 PSI, that's not bad. Is it going to work? Did I actually do anything? Did I make it better? The mass, looks like the mass went up. I must have made some changes previously that I forgot that I made. That's not good. So here we go. We got our mass and our stress. So it looks like I was able to take the stress down a little bit. The mass went up a little bit. So I must have missed the design iteration a little while back, and I forgot that I'd undone that change. So that's, you know, a real simple human error issue, but man, I must have missed out on something. I do remember what that was, though. It was these cuts right here. All I did was make them just a little bit smaller. Instead of 1/8 of an inch, I think I just went to a 1/10. And I think I made this cut depth just a little bit bigger too. So let's say 0.15. Now as I'm making these changes, you know, I might want to capture them in maybe a configuration or something like that. But I'm going to go ahead and just keep them on the fly and see where things go. Now these are all these capabilities. These are all in Simulation Standard, which is a great addition for if you have SOLIDWORKS Standard or SOLIDWORKS Professional, and you haven't been able to upgrade or make the change to SOLIDWORKS Premium. Simulation Standard gives you a lot of capabilities. Here's my mass. Again, looks like the mass has gone back down, not quite to where it was, but my stress has kind of gone back up. So whatever I did around iteration 13 and 14, that was a really nice design. And I can start to go back and really look at my history and my notes and figure out what exactly I did to make sure I know where I'm at. So I'm seeing these trends, I'm seeing this information, and I'm really kind of monitoring the situation. Eventually you're going to reach a point, and this is where I end up usually, you reach a point where you find yourself just sort of oscillating very slightly around where you want to be. The result is there, the result is good, but you're not making any meaningful progress. I can see that, I can measure that, and now I can kind of move on to the next step. So in the next step, what I want to do is start validating that final design. So I'm saying, okay, this is going to work. This should work. Before I send it out, though, before I prototype it, I want to create a more accurate analysis. What I was doing is making the assumption that, hey, you know, it's just going to be held onto these pins, and the pins are really well connected, so we'll bond it. So I want to start looking at some nonlinear contact. I want to look at maybe some longevity, right? We're going to look at fatigue concerns. So I'm going to go back into the study and kind of copy it, but then make it more accurate by leveraging some of the capabilities inside the program. So when you start talking about building a more accurate study, right, that's where I'm going to go in and take a look at nonlinear contact. And so what I did is I changed my contacts to no penetration. Now, all that really means is instead of these being 100% bonded, connected to where there's no separation at all, the reality is they're just kind of press fit. And as I pull up on this handle, you might see some separation around this area. You might see some slipping, or you might see a kind of rock a little bit. And this nonlinear contact, where it's a no penetration contact, is going to give me that accurate solution. I'm also going to change to a material that has a more advanced material property curve. So when I go in to apply the material over here, and I go into my SOLIDWORKS materials, you'll see that not all the materials have accurate information or any information. So in some of these aluminums don't even have a yield strength or a tensile strength, and so I either got to look it up. Or the material information is there, but it's extremely conservative. 3,000 psi is not a yield strength for steel or aluminum. You'll also see somewhere it says SN or SS. That means it has a stress-strain curve or a fatigue curve, and I didn't find a 6061 with a fatigue curve in the material library. So this is one of the great benefits of Simulation Standard, is this fantastic materials web portal. So it's right here at the bottom of the entire list of materials. It says click here to access more materials using the materials web portal. And this is where it's going to take you. You do have to be on a simulation license, so this is not going to work for SOLIDWORKS Premium. You want to be at Sim Standard, Sim Premium, something like that. And this web portal will let me find, for instance, fatigue information for metal being pulled from this global data center. And just hit locate materials, and it gives me a nice long list of materials and material curves that follow and match my criteria. And I've got quite a few. I got 3 pages of results, and as I browse down here, I find this 6061. That's the one I'm looking for, but a very nice selection of tempers and grades. Here's the material model. Here's my various tables and curves, including the max stress and cycles to failure curves. This information is not unbelievably difficult to go find, but man, this saves so much time having to go kind of reverse engineer a graph out of a textbook or out of an old book in the library, or maybe just kind of finding some random curve that I hope is valid and useful, but I'm not really sure. So all this information is coming from useful sources, valid sources, and you just click download, click the little download button right there, and you're good to go. You're in business. And so that's what I did. I came down and I downloaded this materiality material, and it has a really nice SN curve applied. I can overwrite any of the values if I need to, but I'm ready to roll, and I've already run this one ahead of time. So if you look at the stress values, you can see we actually have and I didn't really point this out previously, but the stress values are in a slightly different area than they were previously. And that's because you're seeing a lot of that sort of stretching and twisting and cupping, and so you're seeing tension right along this bottom edge, and it's kind of trying to tear away. And you could probably predict that. I mean, if you were to kind of pull on that and take a look at how it's twisting and deforming, you would understand where that's going to go and what that's going to do. But this is a much more accurate solution than it was when we were just doing a bonded contact. I could also go through and add an H-adaptive study. An H-adaptive study, what that does is allows me to run and rerun the study with a more advanced mesh each time. To go through that, it's in here in the properties of the study, and I can't have these guys fixed. I have to have them deformable in order to get to it. But with an H-adaptive study, you basically say, hey, just remesh and rerun this thing until we reach a really nice convergence. So that's another really useful tool for reaching accuracy. But the next one that I want to do really relates to fatigue, and that's something that you'll see in Simulation Standard that's not in SOLIDWORKS Premium. And there's 2 ways to measure fatigue. There's the easy way, and then there's the thorough way. Now the easy way is my favorite because it's really easy. In this stress plot, and this applies to any stress plot you have, just go and define a fatigue check plot, And, oh, I got to find the tensile strength to do that. Let me go ahead and just apply that material and do that real quick. We'll fix those guys again. And this fatigue check plot, it's going to go off of the infinite life model. So in other words, it's going to say, okay, well, I know, for instance, that this will never yield or never fail beyond this certain level of stress. And so by going through and saying, okay, it's going to be an on-off load, it's a machined surface, so that kind of takes into account any surface imperfections, and we need a minimum factor safety of 2, and the software gives us kind of a pass-fail on the infinite life model. And take a look, it's highlighting that area where the maximum stress was. That's a possible fatigue concern. Now, it's not saying it's going to, it's not saying it's not going to, it just says, hey, this thing isn't going to last forever. It might be 1,000, it might be 10 billion. But you probably ought to look at that if fatigue is an issue. No problem. I've got the ability to run a fatigue study. I'll create a new study called fatigue. Let's see, this is going to be, yeah, we'll just call it fatigue study is fine. And the nice thing about a fatigue study is all you have to do is add an event from one of your other examples. So that final study that I did just a second ago, I'm going to say I want one of those, and I'm going to do 10,000 cycles. 10,000 cycles if you say this many loadings in this many days and this many years. You know, this is about how many cycles I think this is going to see. So I add those cycles to failure and then just run the thing. Now you can do stress, mean stress correction and things like that, but I think the information I got on my fatigue curves is pretty solid. And so what we're going to get is a couple things. You're going to get a life and we're going to get a damage plot. And you can look at it in several ways. Damage plot says after the stated number of cycles, how damaged is it? How far towards the likely failure point did we make it at those 10,000 cycles? And then the life gives us a recommended or a predicted cycles to failure. And once we finish running this, we'll get that information. I'm going to let that run for just a second. And we're going to kind of go back to the overall idea, which is the tools that are in the software to validate the accuracy of your design makes it easy to work with. You don't have to spend a lot of time worrying about material curves, trying to find out whether your mesh is there, trying to interact or understand the complex interactions of nonlinear contact. SOLIDWORKS simulation standard is going to have you covered. So the last thing I want to look at is yet another step back. Anytime you're worried or you're not sure about how the overall system is going to behave, that's where you've got to kind of expand your system. So assuming that the world stops at the end of the handles is not a valid assumption. I've got to take into account the entire system. And that takes a while to do. You never want to run the entire system early. You want to run the entire system when you know it's going to work. Same with prototyping. You don't want to prototype the thing when you're not sure if it's going to work or not. You don't want to go 3D print some pieces that aren't going to work at the end. So let's kind of take a look at what that would look like if I was to run the entire system. So I canceled the fatigue. We'll come back to that a little bit later. So here's my overall system. And you'll see now instead of all these other components being excluded, now they're included. Now these other components, these other pieces are all in there. And it's going to take a little bit longer to solve, which is why I solved it ahead of time. But by running the entire thing, I'm able to get an understanding of where my weak points are, where my problem areas are going to be. You know, you see the design here. We've got these kind of stabilizing ribs. Those guys are going to see some stress. They're going to see some tension, and that might be an area where I'd want to either modify the design slightly, or I may want to maybe change the shape, something like that. The maximum strength happens to be down here on the pin, which is just a stress concentration caused by the mesh. If we go back through that exercise of turning on the H-adaptive or just adding a mesh concentration, that gets cleaned up. But we're able to really understand where some of these issues are going to be. We can also do things like ISO clipping, section clipping. And what that does is says, okay, well, show me the areas in the model of greatest concern. And in this case, we're seeing that the areas of greatest concern are down at the bottom of the case. I mean, we're throwing 500 pounds in this lunchbox. This is going to be an issue. This is going to cause some problems along the bottom. Probably not going to cause any failures, but we need to make sure. We may need to add some stabilization, maybe put like a rigid plate at the bottom to try to carry that load instead of allowing it to be loose at the bottom. But we're also seeing some issues up here around the closures and the clasps, so we need to focus a little bit area on that, make sure we're not going to lose our cargo if we pick this thing up and the latch breaks off. So SOLIDWORKS Simulation is just this fantastic tool to kind of cover every aspect and every part of the process of SOLIDWORKS design. Right? We want to analyze early and often, and that's something that SOLIDWORKS has always emphasized in their simulation products. They put it in the interface to make it as easy as possible for you to switch back and forth, for you to revisit anything you did. We did this once before when we built this as a plastic design. When somebody asked us to upgrade it to a 500-pound handle, we reused a lot of those studies. We leveraged those, and we didn't have to start all over again. We were able to track that performance, see whether we were making progress, see whether or not we're stuck in the mud or we're actually getting there, and whether we made a net benefit of reducing the mass and reducing or maintaining the stress. We were able to do a full validation of the final design. Not only the final design to make sure our mesh and our study was accurate, we also did nonlinear contact to make sure our assumptions were valid. And then we checked for the fatigue life of our design to make sure that this thing is going to last long term. We took that one last step further to do a complete system interaction. The simulation package has the power to run some extraordinarily complex design systems, and we're continuing to see every year the solvers get much more powerful and the solution capabilities are greater. So although early and often you're probably looking at solve times in the 5 to 10 seconds, the complete system interaction, you could set up a study so large it takes hours or even days to run. But you can handle that at the end of the process. That's not something you can do early on. So all this is to kind of really talk about this engineering starter pack. It's an idea of taking a SOLIDWORKS seat, and this could be SOLIDWORKS Premium, or if you don't need things like routing and some of those other packages and capabilities that are inside Premium, you can start with just SOLIDWORKS Standard or SOLIDWORKS Professional. All the design tools are going to be there. And by adding on Simulation Standard, you're going to get every tool that we just talked about and more to get your job done quickly. And one of the big reasons we're doing this is because they have some nice special bundle pricing. So if you are in the market for maybe another seat, maybe you got one more person in your department that needs a seat of SOLIDWORKS, or if you're just starting out with SOLIDWORKS and you've never done this before, this would be a great way to get started. It really does give you a tremendous amount of power for not a lot of investment in software. So contact your MLC sales rep or give me a call. If you have any questions at all about running studies, any license of simulation, or doing any kind of design in SOLIDWORKS, I'm happy to help. Now, we've got some people on here answering questions. If you've got questions, I'm more than happy to take those at this time. But thank you very much.